Transformers without normalization. This is a crazy new paper released just a few days ago. They replace normalization with just a simple tanh function, which is crazy. A reminder for a tanh function, so it has this S shape and it's bounded by 1 and -1, so it never reaches those points, and it goes through 0, 0 point. And this parameter alpha, this controls the steepness of the curve. So if it's 4, then it's very steep, but if it's 1 over 4, then it's very straight or more straight. Then let's remind ourselves what layer normalization is. So let's say we have a vector embedding that 0.1, 0.3, 0.5. And here it says what we like, how we transform, how we layer normalize this vector. But in the end, what's important, you can ignore everything except this is the result. So the mean will be 0 and standard deviation, or variance is 1 per token. So all of these numbers will be between -1 and 1. And if you remember, I just said that also tanh is also between -1 and 1. So in this paper, they just replaced layer normalization with a tanh. And the tanh is much simpler computationally, because for layer norm, we need to compute mean, variance, normalize, scale, and shift. And for tanh, there is just one computation. And layer normalization does the similar thing as tanh. If you see here, the shapes look similar to tanh, with tanh just having those different scaling factors, alphas. So it also looks like an S. So the way you can understand this is there are some values on the x-axis, which is input to layer normalization, and then we pass it through layer normalization and we get some values on the y-axis as output. And you can see that those values on y-axis, they cause this to have similar shape, so the values are going to be similar to what tanh would give. Here we can see the standard layer norm. So we have normalization, where we set the vector, the embedding vector, to have a mean of 0 and variance of 1. And then there is scale and shift. Scale and shift is, I will show you what it is. So imagine this is not tanh, this is just layer norm. So we have this vector that's like a one-dimensional vector with a lot of numbers. This is also going to be a vector that multiplies this vector, same shape. So this is also the same shape vector that's going to be added. So it might remind you of a linear layer where you multiply some variable with weights and bias, add bias. But this is different in a few ways. First, well, it is similar in the way that this is also learned and this is also learned, but it's different in a way that in a linear layer, the matrix will transform the vector size of the variable into different size, maybe expand or subtract, and it's matrix that in a linear layer. And here is just a vector of the same size. And this is also a vector, but in a matrix it can be, yeah, also a vector. Not in a matrix, in a linear layer, it can also be a vector. And what they do is they just replace this normalization step with tanh step, and that's it. And it works better for vision models, for llama, LLM models, for speech, and for DNA. And they also replaced RMS norm with this and say that this works better than RMS norm as well. Here are some differences between layer norm and RMS norm. So the main difference is this calculates or subtracts the mean, and RMS norm doesn't. You can read the rest if you want. Yeah, it's actually funny that in recently everybody has been trying to replace like attention or convolution and those kind of layers, but nobody was trying to replace normalization. One important thing is that this alpha in tanh in this paper is a learnable parameter, where alpha is a learnable parameter. So it's a single scalar number. that's learning to properly scale inputs of this normally or tonnage. It's not a, what do you call this layer now? I don't know if it's normalization layer. Here we have some drawings to understand batch normalization. So we have a batch, or what they call a mini batch. It's a group of sentences. Actually, this is a group of context windows. So each, but to simplify it, is, let's say, just a one sentence. So first sentence, the cat sat, and we have token 0 for the, token 1 for cat, etc. Second sentence, third sentence. Now let's zoom in on one of these tokens, which is going to be cat. Each of the tokens or token embeddings numbers is a dimension. So dimension 0, dimension 1, 2, 3. And then here you see we have second token, which is token at position 1 from each sequence. So it's going to be cat, ran, and like. There's a second word, second token in each sentence. And these are their embeddings. Then we calculate mean for each dimension. So we take first dimension in cat, first dimension in ran, first dimension in like, and calculate mean. We do same for the second, third, etc. dimensions. So then from the dimension we subtract the mean and divide by standard deviation, and we would calculate the standard deviation from the same thing we calculated mean from. So for the first dimension we use the mean of the first dimension, etc. Second dimension we use the mean of second dimension and standard deviation of second dimension, etc. Usually layer norm is used more than batch norm in NLP, natural language processing. One of the main reasons, here you can see many, but one of them is there are different lengths of sequences. So layer norm doesn't care because it calculates within a single sequence and not across the batch.
In this image, you see that we are looking at the vision transformer layer 15 and layer 20, and also layer 15, layer 20. But this one is coloring by tokens. What does that mean? It means so if you see one color, that means those are the features of one token. So there is a token embedding that's long, who knows, let's say 1,000 numbers, but for simplicity reasons I think that's why they just have like maybe 7, 8 numbers here, and each of those numbers in that vector is colored by same color. Now why are some of these dots have a straight line? This is because layer normalization is a linear transformation. So here you see this is doing the normalization, subtracting mean, dividing by variance, and then we have this gamma and beta shift and scale and shift. So that's going to be a linear transformation. Now each of these colors is going to be a straight line. So as you can see, even a yellow one is a straight line. Now we see that red one, for example, it seems like it's not, but that's, I think they color different tokens here, just with these colors to show you something else they want to show you. So if we compare layer 15 and layer 20, we can see that layer 15 has these straight lines a lot more spread out. That means the mean and variance here within the layer is more varied than layer 20. Right images show coloring by channels. So this is still layer normalization. So this is still normalization across the vector embedding. But here we see same color is same channel across different tokens. So first channel in first token, first channel is second token, first channel is third token. And we see that they form these S-type curves. The reason they look like tanh S curves is because layer normalization works such that the higher the value on x-axis, the more it's gonna get squished and it's gonna be made smaller on y-axis. So the shape and length and look of this S-shaped curve is dependent on the variance of the value. So for example, this red curve can have like values, x values between -100 and 100. And so it's gonna be a lot more prominently squished. So yeah, but these purple ones have values between -20 and 20, for example. Then it's not, the S-shaped curve will not be so obvious. And the squishing, because the squishing will not be so obvious, it will look more linear. Because the more squishing there is, the more it looks like an S-shaped curve. So the most important lesson here is that smaller values are not affected too much by the layer normalization, while the larger values are squashed and affected a lot more. So if you think about it, it kind of makes sense that layer transformation creates this S-shaped tanh curve, because the middle layers will not get so affected. The values are close to the middle of the coordinate system, like 0, 0, will not be so affected. But the values that are further away on x-axis will get squashed more. So that's why you get this S-shaped curve. So on the left plane, as I said, each color is from the same token, so they are linear because layer transformation is linear. But interestingly, what they find out is if you plot these linear transformations, they form a S-curve if you plot a bunch of tokens. Integrating dynamic tanh is pretty straightforward. One dynamic tanh layer replaces one normalization layer in attention block, FFM blocks, and final normalization layer. So dynamic tanh, or which they call it DIT or DIT, I'm not sure. It may look like activation function, but they just replace normalization layers. They don't touch GALU and ReLU and activation functions at all. They also observe that there is little need to tune hyperparameters from the original architecture they proposed. So they initialize the scale factor gamma to all ones, all one vector, and the shift factor to all zeros, and then alpha to 0.5, and alpha is the slope within the tanh. So you have tanh of x times alpha. Here they show some experiments. So red one is the dynamic tanh and the blue one is layer normalization, and they seem to be similar or same, maybe a little bit difference here, I guess. They also seem to be very similar here in the training loss. So this is vision tasks. Seems like layer normalization is a little bit better here in the training loss, but it has a lot more computation, so maybe it would be worth to use dynamic tanh. And here on these benchmarks, there is a little bit of improvement while using dynamic tanh on the accuracy. So these are vision tasks. They compare other visual models here. They are pretty same. Actually, they compare diffusion transformer here as well. Looks pretty similar. Then they also pre-train these llama models, which seems to me like they have a lot of compute if they're gonna pre-train 70B model just for one experiment. So the loss seems pretty similar. So their claim is that you can just replace tanh with this. You can just replace layer normalization with tanh, dynamic tanh. Here we can see the change is only a little bit here and almost non-existent compared to RMS norm. And also for speech and DNA sequencing, it stays almost the same.
So the performance may be the same, but speed of forward pass, inference, and training is faster. So for Llama 7B, inference for RMS norm is 2.1 seconds, while dynamic tonnage is 1 second, which is 50% improvement on a layer level. And on a model level, it's almost 8% improvement for inference. And same for training. There is more than 8% improvement for dynamic tonnage in speed. So I don't know if they wrote it anywhere, but from my understanding, this layer is comparing just the execution of this guy versus this guy. So it's not the whole like transformer block layer. It's just this normalization layer speed. So speed of this normalization layer and speed of this normalization computation. This one is 50% faster.
Then they perform some more ablations. So tonnage versus hard tonnage versus sigmoid, and tonnage performs best, although these two also squish. But the most important finding is that you need to have a function that's gonna squish extreme values, bring them down. And all of these functions do it, so they are pretty similar in the results. But identity function doesn't squish anything. So it just, whatever the value is on X, we put the same value on Y, which is why this training pre-failed. So you need to have squishing for stable training. This is essential. So the difference between sigmoid and hard tonnage and tonnage is that sigmoid is squashing between 0 and 1, tonnage between -1 and 1, and hard tonnage is approximation for tonnage that's also trying to squash between -1 and 1, but it's more computationally efficient to calculate. Although it's a little bit worse, not as accurate, because it's just trying to approximate tonnage. Then they tried removing alpha. So you remember, we have tonnage of alpha times x, and alpha is a learnable parameter. And if they remove it, performance degrades for all of these functions. This is an interesting finding. If you see here, during the training, the vectors that this tonnage is normalizing, the numbers in them change in each layer. So if you plot alpha versus 1 over standard deviation, they get that these lines, these values are very similar, which is very interesting finding. So that means that alpha in some way acts as a either counterbalance to standard deviation. So you can say that alpha is learning the value of, or approximate value of 1 over standard deviation to better normalize the vectors. Then they compare dynamic tonnage not only with layer normalization but with other stabilizing methods. And it just shows that their method has the highest scores of all of these other methods.
Thank you for watching. You can help me accelerate AI progress for many people by helping me do this full time. For just $5, I can help 200 people accelerate their AI progress in studying by 2 to 3 hours, which is around 500 total hours of accelerated AI progress. Help me do this full time and help me bring AI, open source, and democratized AI and benefits to everybody. See you in the next video.